In recitation Tuesday, it was clear some of you didn't really have this clearly in your notes. I'm not, and there was some correlation between people who didn't really have it clearly in their notes and people who were using their phones a lot during lectures, so that at least is coherent. Nonetheless, you need to know this. It should be showcased in your notes. It won't be on equation sheets. Yes.
Is that K kinetic energy?
Is what?
Is that K kinetic energy?
K is kinetic energy, and E without any subscripts or anything tends to mean total energy. So K stands for kinetic energy. So we spent the entire period talking about the energy principle applied to systems that consisted of only one object. So one object was the system and everything else was the surroundings. And the surroundings did work on the system and changed its energy. And we discovered that work could be positive, so it could increase the energy of a system, or it could be negative, kinetic energy of a system, or it could be zero and not do anything to the system. And there were two ways for it to be zero. One was if the force was perpendicular to the displacement, because in this work equation, this delta R is the displacement through which the force acts. And so if a box is sliding this way, but you're pushing down that way, the force you're exerting is perpendicular to the displacement. You're not doing any work. A spacecraft orbits the Earth in a completely circular orbit at constant speed. The force is always perpendicular to momentum and then therefore perpendicular to displacement, and therefore that force doesn't do any work, which is consistent with the fact that the spacecraft isn't speeding up or slowing down. There's another way a force can do no work, which is kind of an interesting one. So if I jump up, so the floor exerted an upward force on me, but how much work did that force do? Did that force supply the energy that got me up in the air? It didn't, did it? How far did the point where my feet touched the floor, which is the point of application of the force, how far did that point move? Essentially zero. So although the floor was exerting a force on me, it did no work. So the change in my kinetic energy must have come from chemical energy inside my body that was converted to kinetic energy as I jumped off the floor. And we'll do a lot more with that later, but the point here is that you have to think about the point of application of the force and how much the displacement of that point when thinking about work. Now, when we talk about things like gravitational forces or electric forces, we're considering the point of application of the force to be the center of mass of the object. And so the center of mass of the object, how far that moves. What do we do if a force isn't constant? So a varying force. So we compress a spring and then let the mass go, and the mass moves that way. By the spring is changing because the force depends on the stretch of the spring, right? So we can't just so if we wanted to know the work done by the spring from the time the block was there till the time it was there, we could take the force that the spring is exerting on the block here and multiply by that delta x, but that would be an overestimate because the force is decreasing in magnitude. We could take the force here, but that would be an underestimate. We could take the force somewhere in the middle as some sort of average. Or what we could do is we could divide up the displacement into little teeny steps. In this case, we're taking little steps in distance, not little steps in, but it's the same thing we've been doing all along, f delta t's. Well, we can do f delta x's. And so the work here would be the sum of f1 delta x1. So we calculate the force, say, at the middle of this interval, delta x1 plus f2 delta x2, plus we'd calculate the force at the middle of this interval, f3 times that displacement. And so if we broke it down into little steps, we'd actually get a much better estimate of the work done by the spring. Now there are times when we have a force and a displacement that's actually tractable algebraically enough that we can actually just convert this into an integral by taking little teeny steps. And so the work would be the sum of, we have a minus k sub s times x, where we're again taking our coordinate system where x is 0 at the relaxed when the spring is relaxed, like we did the other day. And if we take little dx steps, then we could convert this to an integral from the initial x to the final x. And we can always write this as an integral. Whether we can evaluate it analytically is a completely different issue. And so what would this integral come out to? Okay, so basically ks is a constant, right? So it comes out, we have an x dx. So the integral of x dx is indeed a half x squared. We have this minus k sub s here, and we're going to evaluate it from x initial to x final, right? Right, thank you. And so so the sign of this work is going to depend on x initial and x final. So if that's 0 and that's 2, the sign of this work is going to be negative. And that makes sense because if the spring went from its relaxed length to a much longer length, delta x is that way, but the force is that way, so the spring is indeed doing negative work. If, on the other hand, we went from 0 to -2, then the force and the displacement would be in the same direction, and we'd end up with a positive number here. The spring's doing positive work. Okay. Or 2 to 0, sorry, 2 to 0. So we went from 2 to 0. So we're here, we go back that way, okay? So here's one of the cases when we can just do this with calculus. And we can always write varying force work as an integral, but there are sometimes some integrals you just can't evaluate analytically, and so we'd end up going back to our step-by-step numerical approach, which always works. And if you take small enough steps, you're going to get a really good answer anyway. So varying forces, and we'll come back to this in a little bit. So now what I want to talk about, another thing that can happen with, so basically we're moving toward a situation where we're talking about systems that have more than one object in them. And what I want to talk about first is a situation where the rest energy of an object changes. Now, how can the rest energy of an object change? Well, one way the rest energy of an object can change is in radioactive decay. So here are some examples. It turns out that although neutrons are super stable inside atomic nuclei, if you just have a neutron all by itself sitting there, it'll last on the order of 15 minutes before it totally falls apart. And when a neutron decays, it falls apart making a proton and an electron, thus going from a situation where we had zero net charge, to a situation where we still have zero net charge, because it turns out another really important law is conservation of charge. We think the net charge of the universe doesn't change in processes, in any kinds of processes that go on. And it also makes a particle that's really hard to detect called an antineutrino. So basically, this is neutron decay. It's called beta decay because back in the days before people understood that what was coming off in these processes was electrons, they called them beta rays because they didn't know what they were. So it's called beta decay process. And so in our initial state, we've got a neutron, but then we don't have a neutron anymore. We've got 3 other particles. So the identity of the system has changed. And presumably, the energies of all these particles have to add up to the initial energy of the neutron, and if it was at rest, it adds up to the rest energy of the neutron. So that's one kind of process where we have changes of rest energy. Another is fusion. If we have hydrogen plus deuterium, a process that occurs in the sun, they can react to form helium-3. And we also get from that a photon. This kind of a photon is called a gamma ray. So what's a photon? A photon is a very interesting object. Photons are only kinetic energy. So a photon is pure kinetic energy. So a photon is what we call light. It's a particle of light. And we use light very generally here. So when we talk about light, we're talking about not just the kind of light we can see, but light of energies higher than we can detect and lower than we can detect. So we're talking about gamma rays, X-rays, visible light, infrared, microwave, radio, that kind of. So, and so all it's got is kinetic energy and momentum. It turns out photons also have momentum. And this just isn't like baseballs and basketballs and things like that. It's one of the really intriguing things about the microscopic world, that photons are just not like ordinary macroscopic objects. And in fact, we'll see next semester that they even have some of the properties of waves. So photons are very cool. So as Charles pointed out yesterday, we can't use gamma MC squared in relationships involving photons because they have zero rest mass. So what relationship do we use? Well, an equation that you can derive starting from c squared and momentum equals gamma mv is the relationship for any object, the total energy squared minus the product of the magnitude of the momentum times the speed of light squared is equal to mc squared squared. This is actually question 8 at the end of the chapter, and I expect some of you to go and do it just to convince yourself that it's correct. And for a photon, so this is always true. And for a photon, since this term is 0, the total, so E squared equals PC squared, or E equals PC for a photon, which is often a useful relationship to keep in mind. And a lot of these processes, these decay processes, do produce photons. Another interesting process is if you take a low energy neutron, a very slow moving neutron, and you shoot it at a uranium atom, and this is, then you get what's called fission, and it can fall apart into lots of different kinds of things. It could be barium and krypton and 3 neutrons. So and this is one of the problems with fission as a power source. These neutrons can go on and interact with things in the container and make that radioactive, so they can do all sorts of things. Or you could get palladium and some neutrons and whatnot. So change of rest energy involves a change of identity. So let's actually work out an example. Let's use neutron decay and apply the energy principle to it and see what we get. So one of the questions we might ask is, what is we find the total kinetic energy of all these particles. So find now, in this kind of calculation, because the mass of a proton or a neutron or an electron is so small, instead of using joules, we often use a unit of electron volts. So EV as a unit of energy. And so we have 1 EV is equal to 1.6 times 10 to the negative 19 joules. And so you'll see energies of particles expressed in EV or kilo electron volts is 10 to the third EV, or MeV, million electron volts, 10 to the sixth EV. And so the rest energies of the particles involved in our, I just want to copy these numbers down correctly. So the neutron is 939.6 million electrons, is 938.3 million electron volts. The electron is 0.511 million electron volts, and the neutrino has an extremely small rest energy. It's we used to think it actually was like a photon. It used to be thought that neutrinos were like photons, and they had 0 rest mass. But we now know through some experiments that it's on the order of 1 eV, so 10 to the minus 6 times smaller than all the others. In fact, this is an interesting reaction, because this was first observed in the early part of the 20th century, beta decay, and people found protons and electrons, and there was a problem because the energies didn't add up right. And we'll see how applying the energy principle could tell you that in a minute. And Wolfgang Pauli in 1930 predicted that there was a particle, another particle coming out that was obviously neutral because it wasn't interacting electrically with anything. And it also didn't interact by the strong force, so it didn't interact with nuclei. And so he called it a neutrino. But the fact that it's not electrically charged, so it doesn't interact with protons or electrons, and it doesn't interact with nuclei via the strong force, means that they're very hard to detect. And so it wasn't actually until 1956 that they were finally detected, and I think there was an experiment in an abandoned gold mine. I think it was the Homestake gold mine, actually, in South Dakota, where so they interact by the weak interaction, which means you need a lot of stuff for it to interact with before you get one interaction. So they had a giant vat of, I think, carbon tetrachloride buried down in this mine. Why in the mine? To screen it as much as possible from other stuff coming in from the atmosphere. And they were finally detected. And it wasn't until very recently that we got a handle on the fact that their rest mass is not quite 0. And one of those experiments was called the Minos experiment, and it involved generating a beam of neutrinos in Argonne National Laboratory just outside Chicago and sending it underground where it didn't interact with very much of anything to a mine in Minnesota, a Sudan mine in Minnesota, and that experiment, because they needed a long distance, because it turns out neutrinos tend to change identity. They go from one kind of neutrino to another as they're traveling along this distance. And so it was only, that was one of the first experiments that proved that neutrinos had a tiny but non-zero rest mass, actually. So let's see so we want to find the total kinetic energy of all the products. So how would we write the energy principle for this system? All energy problems are exactly the same. You just start by writing down the energy principle, and then you write down the terms you know, and then you see what's left. So what do we choose as the system here? So clearly the neutron is our system to start with, but then there isn't a neutron anymore. So what we'll choose as the system is all particles that exist at this moment. Okay? So system all particles. And so the energy principle we'll write as E final equals E initial plus work done by the surroundings. Well, this is a pretty process, and it's very quick, and so there probably isn't any work done by the surroundings. So what terms do we put in here? Yeah, Connor?
Can you just repeat what you just said real quick about work? Yeah.
Well, what is there in the surroundings? I mean, if we're in outer space, nothing. If we're near the Earth, there's certainly the Earth. But in the time that this happens, the gravitational force just doesn't have a chance to do much. This is kind of like when we talked about collisions. Times that we could neglect other external forces. And now we have to choose initial and final states. So our initial state is just the neutron. And our final, and it often helps to draw a simple diagram, and one of the reasons is it helps your bookkeeping when you're writing out the energy equation to make sure that you haven't missed any objects or interactions that should be in your equation. So the final state would be a proton and an electron and a neutrino with some non-zero speeds because they have kinetic energy. So they're born with kinetic energy here. And so let's write this equation. The initial energy has only two things in it, right? The rest energy of the neutron and the kinetic energy of the neutron. And we'll say that, so we'll say m neutron c squared plus kinetic energy of the neutron. But if the neutron's at rest initially, that's going to be 0. And what are some of the things that go on this side? So the rest energy of the proton plus rest energy of the electron plus the rest energy of the neutrino, which is really, really tiny, plus, what else? Are they at rest? No. So what else do I need? Kinetic energies. Kinetic energy of the proton plus kinetic energy of the electron plus the kinetic energy of the neutrino. Okay, so where is our unknown in this equation? What is the thing we're trying to calculate? Well, what's the problem statement? Yeah, total kinetic energy of the products, right? So that would be that sum. Yes? Yes. Okay. Well, that means we better know everything else, and do we? Yes, we have this clever little table here of all the rest energies of all the things we're going to need. So we it looks like we have, just rearranging this equation a little, I'm just going to write K total for that sum because it takes up less room, is equal to the mass of the neutron times c squared minus the rest energy of the proton and the rest energy of the electron, because the neutrino isn't going to show up here being 1,000,000 times smaller. And so we have the total kinetic energy of all the products is 939.6 MeV minus 938.3 MeV minus 0.511 MeV, which comes out to some number. I think it comes out to 0.8 million electron volts. So what do we just do? The rest energy of this whole system decreased, right? Because it turns out the rest energies of the products were actually less than the rest energy of the neutron. And where did that energy go? It went into kinetic energy of the products. And that's E equals mc squared at work. I mean, we converted mass here to kinetic energy here. So that's so questions about this? Yes.
Is it possible to predict like the direction that the particles will be traveling?
So the question is it possible to predict the direction the particles will be traveling? And the answer is that the energy principle by itself, because it involves scalars, gives us absolutely no information about energy, about the directions, right? But we do have a principle that talks about directions, and that's the momentum principle. And so the momentum principle would tell us that so P final is P initial plus the net force exerted by the surroundings times delta T, and that's 0 during this fairly fast process. Now the initial momentum of the neutron was 0. So that tells us that the momentum of the proton plus the momentum of the electron plus the momentum of the antineutrino have to add up to 0. And that's as far as we can go without some measurements. But if, for example, we had a detector that detected the emitted electron and said, well, it was going that way because that's where the detector is that found it, and a detector that said, well, this proton was going that way, then we would which the direction of the momentum of the antineutrino, right? But we just don't have enough information without some measurements to know anything except that the total momentum of the system had better be equal to the initial momentum, which is one reason I tried to show particles going in different directions. Yes?
So you said that because the sum of the mass, the resting energy of the protons and the electrons was less than the energy for the neutrons, is it ever possible for it to be greater and we get a negative number?
So I'm not sure what a negative rest energy would mean. So the energy principle tells us that the final energy has to be equal to the initial energy plus inputs. So one thing we could do is take some particles with really large kinetic energies and slam them together to make something more massive. So the product, so we could have, if we took the kinetic energies plus the rest energies of the initial things, we might be able to get a more massive thing out at the end. But I think that doesn't even happen in fusion reaction, actually. I think we still have some rest energy converted to, yeah.
How come when the neutron separates from the proton, electron, and neutrino, the proton and the electron don't attract to each other?
Okay, so that's a really good question, and it's almost a segue into our next topic. So how come when the neutron disappears and we have a proton and an electron and an antineutrino, which doesn't count, the proton and electron should be attracted to each other, shouldn't they? So shouldn't they just stick together?
Is the kinetic energy greater than the force of attraction?
Yeah, so the reason that they don't just stick together is they're born with lots of kinetic energy and momentum in directions that take them away from each other. And so they're not going to stick together at first because they're moving away, but they are attracted, so they will be slowing down as they move. And depending on how great their energy is, they may be slowing down for a really long time before that force is enough to start them back toward each other. And stuff could have happened in the meantime. There's usually stuff to interact with. So they do interact. They are attracted. Okay. This brings us to our second topic, which is how do we consider interactions within a system? And to talk about that, we're going to go back to a really, really simple system, which is we're going to throw a ball up in the air. And what we're going to do is we're going to actually look at this system two ways. We're going to look at it as, we're going to take the ball as our system. But then we're going to say what would happen instead if we took the ball plus the Earth as the system. So there was basically nothing in the surroundings. How would we do the energy accounting? So that's the game we're going to play. So here's the first question. We throw a ball up into the air and it goes up a distance delta y. So the ball is the system. The Earth is part of the surroundings. So what's the work done by the surroundings on our system? Okay, if you don't know, talk to your neighbor. Otherwise, answer the question. Okay, so what's the answer? 3. 3 is correct. So we have delta y is positive, fy is negative. It's a minus mg. So the work done by the surroundings is a minus mg delta y, and the kinetic energy of the system decreases. The ball slows down, right? Okay, so that all hangs together. Now let's consider the ball, the same situation, but the ball plus the Earth as the system. Okay, now how much work is done by the surroundings? Yep, 0. 0. So the answer is 1. 0 work is done by the surroundings. Okay, so 0 work is done by the surroundings, but how did the kinetic energy of the system change? So we have work is 0. What happened to the kinetic energy of our system? Okay, what's the answer? This is a straightforward question. It's not a trick. I mean, what happened to the kinetic energy of the system? It decreased, didn't it? Because the kinetic energy of the Earth didn't change much, negligibly. But the ball, as it's going up, is slowing down. So the kinetic energy of the ball part of the system decreased. But work done by the surroundings was 0. So we have a problem with the way we've... So the energy principle, E final is E initial plus work done by the surroundings. If that's 0, then the energy of the system shouldn't change, but it did. And so it looks like there's a piece of the energy of the system that we are not counting. And that piece of the energy of the system that we're not counting is called potential energy. And so if we write the energy principle this way, the change in energy of our system should be 0, then we had the kinetic energy, change in kinetic energy of the ball plus the change in something else about the system has to be 0. This thing is called, is symbolized by a capital letter U and the potential energy, and it's energy associated with the interaction of two objects inside our system. So now we actually know what that number has to be in this case. When we considered the ball as the system, change in kinetic energy of the ball was equal to a minus mg delta y. So this is a minus mg delta y. This has to be a plus mg delta y to come out to 0. And it's equal to the change in potential energy of the system is equal to the work done internal to the system. So the Earth does work on the ball. We can't count it as and it's got to have a minus sign because the sign changes. So basically, what we've done, we could say the change in energy of the system is equal to work done by the surroundings minus work done by, let me rewrite this so it looks better, minus work done by forces internal to the system is equal to work by the surroundings, and we call this a change in potential energy. So we're basically putting everything in this form of the momentum principle. We're putting everything related to the system on the left-hand side and everything due to the surroundings on the right-hand side. So therefore, it looks like for a system with several objects in it, yes?
So what we're saying is that the change in the potential energy is that negative work of the interior of the system?
Yes. The work, it's the negative of the work done by forces internal to the system, by objects inside the system are exerting forces on each other. Okay? Now that means that if we have one object in our system, there is no potential energy. So a one-particle system does not have potential energy. It's just got rest energy and kinetic energy. It's only a system composed of more than one interacting object that can have a potential energy, and that energy is associated with interactions of the object within the system. So for a multi-particle system, the energy of the system is equal to m1 c squared plus m2 c squared plus kinetic energy of object 1 plus kinetic energy of object 2 plus the potential energy associated within the interactions of object 1 and 2, and the potential energy associated with the interactions of object 1 and 3, and the potential energy associated with objects 3 and 2, and so forth. So now there are a lot more energy terms when we calculate the the energy of a multi-particle system. As for a single particle, the energy of the system is just mc squared plus the kinetic energy. So the rest energy plus the kinetic energy. So let's see how this plays out and how we calculate it. So we already saw that near the Earth, near the Earth, the change in potential energy of the system of the ball in the Earth was basically equal to mg delta y. But let's see what it would be in a more general case of two objects interacting. Yeah, we have time to do this. Two objects interacting gravitationally like a planet and a star. So let's consider two gravitationally interacting objects that are a distance, we'll do it with x here. They're a distance x apart. And then they move, so they're a different distance, x2 apart. So the work done internal to the system is, we'll call that F1 and that F2. So here's this here's delta x1, the distance that moved, and here's delta x2, the distance that guy moved. So it's F1 delta x1 plus F2 delta x2. But F1 and F2 are equal to each other because this is a gravitational force, so the magnitudes are equal. And the force is in the direction of displacement, so it's basically equal to the force times, it's as if this guy had stayed still and that guy had moved the full distance. I mean, we're just interested in the relative change in relative distance here. So the change in potential energy is going to be the negative of the internal work done in this system. And that's going to be equal to minus in general fx delta x here. Now, to solve this analytically, we can rearrange this. So we can say the change in potential energy with respect to x is equal to minus the x component of the force acting on the system. And obviously, if we take this in instantaneous form, we're going to get rate of change of potential energy with respect to x is minus fx. This derivative with respect to position is called a gradient. So rate of change of potential, the negative of the force is the gradient of the potential energy. So more generally, we can write it, because we're not always in the x direction, FR is minus du dr. And now our job is for the gravitational force to find an expression for u that works. So the gravitational force is minus gmm over r squared, and that's equal to the derivative with respect to r of potential energy. So we basically need an antiderivative here, right? So what is it that we could differentiate with respect to r to get this?
What was the question?
Let's find, the question is, let's find an expression for u that when we differentiate it with respect to r gives us that. What?
R squared.
So here, this, let's rewrite it as minus g m m r to the minus 2. So we're going to have, so the derivative r to the minus 1 is what? Minus 1 r to the minus 2, right? So making sure to get our signs right. So these two signs cancel. And so we get u is equal to a minus g m m over r. Now, is that something you have to memorize? No. But we do need to be able to work with it.
Are the negative signs?
Well, notice here that we have minus gmm over r squared equals minus. So we've got a plus here, and so we've got this minus sign here, right? So the change in potential energy is going to be from some situation to some other situation is g m over our final minus a minus g m over our initial. Now note that this thing is negative. So gravitational potential energy is negative. That's okay. It's all right. It can be negative. It's okay to have negative terms in the energy equation. It all comes out all right. So let's quickly apply this to solve a problem and see how this works out. So we have an asteroid and a rock, and the rock is falling toward the asteroid. And the mass of the asteroid is 2 times 10 to the 16th kilograms. The mass of the rock is 8 kilograms. And the radius of the asteroid is 10 kilometers, sorry. And it starts out 100 kilometers away with an initial speed of 5 meters per second. And so the question is, how fast is the rock going when it actually hits the asteroid? So how do we solve a problem involving the energy principle? We write down the energy principle, right? E final is the initial plus work done by the surroundings. And in this particular case, we're going to take the rock plus the asteroid as the system. So we can... So that's going to be 0. So the final situation is going to be, what do we have here? We have the mass of the rest energy of the asteroid, the rest energy of the rock, the kinetic energy of the asteroid, the kinetic energy of the rock, and what else? The potential energy is, and we know the rest energies aren't changing, so let's actually not include them. So these are final kinetic energies. We have the initial kinetic energy of the asteroid, the initial kinetic energy of the rock, the initial gravitational potential energy. Now, how else can we simplify this? The asteroid is clearly a great deal more massive than the rock, so how much does its kinetic energy change? Not much. So where's our unknown? The final speed of the rock. So what term is it in?
Decay final.
So it's here, isn't it? So that's what we want. So basically, the final kinetic energy of the rock is equal to plus, so 1/2 m rock v final squared plus a minus g mass of the asteroid, mass of the rock, over the radius of the asteroid, because that is equal to 1/2 mass of the rock v initial squared plus a minus g times the mass of the rock, mass of the asteroid, over what was it, 100 kilometers, so 100 times 10 to the third, so and this is 10 meters squared. And we know all these things. We know G, we know the mass of the asteroid, we know the mass of the rock. So we could actually plug them all in. We're careful about initial and final distances being in the right location. And we can solve for the final speed of the rock, right? Yes?
Was the R the denominator squared?
Oops, it shouldn't be squared. Thank you. Good call. Too many forces. Yes?
I think its final kinetic energy would just be equal to its current kinetic energy plus its potential energy in the system, since its final potential is actually 0.
Final potential energy is not 0, because when we consider gravitational forces, remember we're considering, it's as if all the mass were compressed into a point at the center of the spherical object. And we're not at the center of the asteroid. We're at the radius, which is 10 meters away. If we were at 0, in fact, the potential energy would be infinite. So that's probably not that good. So the potential energy is not 0 at the end. And the potential energy, we don't have time to do this. We'll have to do it next time. But the potential energy of you know, when we talk about delta y, mg delta y minus being the change in potential energy near the Earth, that's the change in potential energy. But the actual potential energy is, there's a minus g, mass of the Earth, mass of the object over the radius of the Earth, plus mgy that comes into it. So it's only that change that make it look like, yes, Andrew.
How do we know which distance to use for neutron?
Well, how do we know which distance to use? Because we're being really careful to write final on this side and initial on that side. And it starts out 100 kilometers away, and it ends up 10 kilometers from the center. Okay, so we will do problems like this afternoon.